Okay, so I'm going to begin my demo right now. So today I'll be covering a CTF reverse engineer challenge, right? So the idea here is that the competition gave us this binary, and I threw it in Binary Ninja. And the reason I threw it in Binary Ninja was I wanted to first cover what Dave touched on his previous reverse engineering. And that's this tactic of trying to find where is the start of the program? Where is the functionality going to start executing from the program, right? So that's what we have to figure out first. And so I sort of want to go through that process so the viewer sort of understand what's going on. So basically, first you have to think about, okay, how does the operating system, when you run the command to execute something, say the binary name is foo, and then you run foo, right? So that's what you type in your command prompt. What happens there? So what happens when you sort of start running a binary is the operating system has these sort of loading processes to load that binary into memory, and then part of it is once it loads into the memory, then sort of give control of execution to the instructions in memory. So that's at a very high level of what's going on, and you'll see some of that sort of plugging type of instruction code within the binary itself, right? For all the different loaders, and then the different activities that it does is it has to sort of resolve dependencies. So then it's like, okay, there are certain libraries that it has to sort of link in with your processes. It has to do all of that, but it has to get that information from somewhere. One is the environment already in the operating system, and the other is data within your binary itself, right? So that's why we have these this first function here called underscore start. See, you see it do a little bit of like libc kind of initialization kind of stuff, and then it calls this a libc start main. Right, so first we know of underscore start, and then we see, okay, it's calling libc.main, but so we know that ultimately we want to get to this main function. This main function is the first block of code within our binary that developer wrote themselves, right? So we really care about eventually getting to that main. So what's happening here, right? Main is being passed, the address of main is being passed into the register RDI. And then after it passes the RDI, it calls this underscore libc start main, right? So let's go there. So what we're seeing here is like, this is a jump table to other functions. So I imagine, so this is a global offset table. Is this what this is? And so within here, you have these pointers to these different functions. So what it's doing is that, you pass in this argument within the RDI register, then it calls here, and then it jumps to this portion within the global offset table, and then it's going to use that RDI argument to then call your main function. I believe that's what all that is doing, right? So we go through all that, and then over here, right, that's how it finally gets to this main. So now we're in main, right? Okay, so we're in main, and okay, this is a good time. So what I did here is that I have this sort of analysis box with this disassembler, right? So I loaded the reverse engineering binary challenge into this disassembler to sort of try to get a feel of like, okay, what is actually within the instruction code? So this is the disassembler. But now we're going to jump to our box that actually has the binary. Okay, come on. Okay, so this is the box that actually has a binary, and the name of the binary is REV, right? So it's very typical for these kind of CTF challenges. They'll give you a binary, you could download it, and then you do your analysis to try to figure it out, right? So first off, we have this binary. So what is the first things we can do is we could run some commands to sort of figure out, okay, what is this binary about, right? So one of the really good commands is to run file on it. File will show you what kind of file it is, and in this case, it's an ELF 64-bit. So it's like, okay, so this is a Linux binary, right? So I should be able to run it on a Linux 64-bit operating system, right? So there's like, okay, cool. So then, okay, it's ELF binary. Let me try to run it. I run it, and then I get this error: permission denied. So what do you think the issue is here?
So, I mean, the first thing that I would check is what's the permission level?
Exactly. That's exactly right. So this is the permission level. So you run ls, get permission level, and you will notice there's no execute permissions, right? So you have to fix that. So right now, for the more advanced folks, they might think like, oh, this is so trivial, or this is so obvious. But what I've seen a lot in the different red team, blue team competitions, and also within just doing pen testing and red teaming, you run into these kind of issues. And unless you in the way I'm sort of trying to present this is like, I'm trying to present a methodology where you run into problems and then you ask the right questions and then you try to solve the questions and the problems that come up, right? And if you have that kind of mindset and that kind of methodology and workflow, it's going to serve you really well within penetration testing and within reverse engineering and also within red team. So that's why I'm like showing you these steps that for more advanced folks might be very obvious, but at the very advanced level, their methodology is very similar to sort of the type of problem solving that we're doing for these very simple problems. So that's why I want to sort of run through that process, right? So now we sort of, okay, it can execute it. So we can execute it. It's asking for a username. So I'll call it, Candy, and then it asks for a password. I don't know, I'll call it, password maybe, and login failure, right? So we ran it. And so by running it, now we get a basic feel for what it's trying to do, right? So it looks like it's trying to get a username and password. And then based on that, you either get a login fail, and we're guessing, okay, if we put in the right credentials, we'll get a login success, right? So if we go back to our reverse engineering, and this is, so we see main here, and let's look at it from a high level what it's doing, right? So we see main here, it calls this take input, check user, and then based on calling these functions, it then does a comparison. And then based on the comparison, you either get that login failure that we saw, or it goes down this different path if we get the credentials right, and then it will cat the flag file, right? So at a very high level, this is what's happening. So for us as sort of wanting to sort of figure out this challenge, we sort of want to identify what are the potentially interesting functions that we want to look at. And, right off the bat, this check user is probably a really good one. So now, I sort of show you, I showed you binary ninja, but now I want to sort of switch gears to this other reverse engineering, because now for this part of the demo, this is going to help us more, right? So right now I'm showing you IDA Pro. And again, right, very similar. We start here. Let's just jump to our main. So now we're in our main here. And the reason I wanted to show you IDA was, okay, we were interested in this function right here, check user. Let's jump to it, check user. And let's check out what's happening here, right? At the very high level here. So for those who are new with IDA, this bottom here, the bottom left, this gives you a view of sort of the whole data structure, right, of this function. And then in here is sort of where you get more of a zoom in and you can like look at specifics. So right off the bat, right, it looks like number one, it's moving this important variable called creds2 into your RAX register. That's number one. And then check it out. This is another really important one right here. So basically, it's so what's happening here, right? So it's moving this other variable called S2. And what IDA is really cool is that IDA will jump into that memory location and then it will give you the value there. So the other way of doing this, and I'll jump back to it once I get back to my Ubuntu box, but in IDA, so this is what it's doing, right? So if I jump into the S2 variable, jumping into the S2 variable, this is the value of the S2 variable. It's this Palash2, right? And then you see some other values for these different variables. For instance, command, right? It's this cat flag. So that's what's happening here. That's what IDA is doing, is dereferencing this variable, and then it's showing this variable as a comment, right? So so from what we're seeing, it's doing this comparison, and then based on this comparison, if we jump down here, so this is a failure block, right? So if it goes down to this failure block, it would just return. So what my guess is that this first block up here is checking the username. So what it's doing is it's checking the username. If the username is not this Palash2, it's going to fail. But say you enter Palash2. If you enter Palash2, this test will be 0, then you jump to the 0. Then you go through this mess of a block right here. You're doing all of these different assembly code, right? Shift right, add, subtract, move, move 0, move sign, add, multiply. So we're seeing a lot of different different mathematical functionality based on some different values. That's what's happening. So And sort of for another view of this, I can show you what that looks like within Binary Ninja. Again, right? A lot of move instructions. And so in theory, you can figure out exactly what all of these operations are doing, but it's extremely tedious. And it could take an extraordinary, very long time, and you have to have sort of a lot of experience doing this to do this properly. So the benefits of this is one of the reasons I really love Ghidra, and IDA Pro also has this as a very expensive plugin, but it has the ability to generate pseudocode. So all of that long instructions, now you have the pseudocode, right? Ghidra will have something equivalent as well. So what that check user function is basically doing is right here, right? It's first comparing Kalash to, and then if it's true, then it's going to go into this function to do more processing, right? So we have these two big values. So it looks like there's these two big numbers, and then you have a for loop here, right? From 0 to 9, you're doing a lot of mathematical operations. In this case, for this variable v6, you're doing some multiplications, and then right here, you're doing an addition and a modulus operation. And then finally, this third variable, it's doing a modulus plus some addition and then some additional modulus, and then raising it to the power, right? And then so what's all of that? So it does all of that, and then it's doing, so after it finishes all of that, right? So basically, it's bringing this 9 times, and then it updates all of these variables here, v2, v3, and v4. And then finally, when it finishes, it pops up right here. And then it checks if you're v4, if after all that computation, your v4 is equal to 0, then it's going to return true. This is kind of stupid the way, like, this isn't good. This is not readable. This is not the best way of writing this code. But basically, it's saying if this v4 is equal to 0, return true. If v4 does not equal to 0, then it returns false. And again, right, and then finally, right, there's a return statement at the very bottom here. So what does that mean, right? So let's jump out of this program right here to see what happens for the call to this check user. So let's jump one. So we're back in main here. So what happens with check user, right? So check user is so the return value of a function is stored in EAX. So it's storing EAX into some memory location, and then it's comparing EAX to 0. And if it's 0, then it jumps to the failure condition right here. And if it's not 0, aka true, then it'll print out the flag, right? And this is the little bit of detail that's very important because it can be very easy to get confused here, right? So what is true? What is true in a C program? True is a non-zero value such as 1. So basically, if we put in the right password, EAX will be some non-zero value, probably 1, and then 1 will be compared to 0, and that will compare to as non-zero, and then it jumps down here to print out the flag. That is what is happening at the assembly level, right? So that's kind of a mouthful, but it's very important to sort of understand that detail. So let's go back to our pseudocode here. So, right, the normal way of doing this is you would have to encode this kind of you would have to do some kind of mathematical operations to figure out what values for all of these different variables, all these different variables you need, so that when you crunch it to this function, will give v4 is equal to 0. That's what it is in a nutshell. And that is I believe that is extremely hard. And so this is where my earlier one of the earlier demos, I showed off the very powerful ability of Z3. And let's go back to the earlier example of the Z3 I showed, right, at an earlier learning session that we did together. What we did earlier with Z3 is that we gave a bunch of mathematical equations, and then we asked Z3 to solve it. That's the ability that Z3 gives us, right? So the very first example I gave very early, super simple, right? X plus Y is equal to 7, find 2 values so that X plus Y is equal to 7, super simple. But now what we have to do with Z3 is to solve these kind of equations, right? This is way more hard. We have two hard-coded values, and then all of these different mathematical, so we're gonna have to figure out, can we do this with Z3, right? So let's jump over here, and over here is how I've encoded it. But let me sort of walk you through it, right? So first off is these 2 values right here. 38, this long value right here. So let me copy that. Here, let
So
me just copy. What's up?
That's a long integer?
Thank you. Yeah, that's a really good question, because you have to be careful about different tools. Some tools will show values as integers. Other tools will show it as hexadecimals. And then sometimes it could have different representation. So be very precise about what is the format of that number, and because that could bite you. And as I sort of walk through, you're going to need to know that that is an integer. So yes, so let's copy this. Yikes, let's copy these values here. We copy it, and then we jump over here, and we go into our code. Yes, we go into our code here. Okay, I think the best place to plop it is we'll plop it here. Okay, so that's there. Because this is Python. Okay, let's just brute force this guy, comment all this stuff. I could do a very cool Vim check and replace, but I just don't have the brain power for that right now in the demo. But okay, first off, right, is this long 3/8 decimal. And what that, how you represent that. So first off, let me sort of give some context here. So the data structures in Z3 are very atypical from other programming languages. And this isn't a good time for me to sort of jump into details, but basically to get to some of those bigger numbers that are used as an array, we have to create this bit vector thing. So that's what this bit vector thing is, right? Very messy. You have to give it the right size. But again, the part that I think is sort of very good for us to sort of focus in on. So the very easy stuff, right? So within the code, we have these different variables: v6, v7, v2, and v4. If I jump here really quick, so you can see right here, right? The different v2s to the v7s. These are variables, right? And for here in this code, I guess I should probably have also called it v1, v2, but for my case, I'll call it a, b, and c. So that's what a, b, c, and d are. But that big number that we have originally here for v6, 3/8, it becomes this array right here: 46, 56, 52. So the challenge here, the question here that you're gonna have to figure out is, how does this number 3/8 all the way up to 9985 become this 4956? What do you think? Why is that the case? What's the relationship here? How did I convert it? Is it sort of the better question?
Well, I mean, so I'm thinking back to, you know, what do you actually have in the code? So
yeah, so here,
capital J as your variable. You set that as your you set that as an array for this bit vector and this bit sorting. And then I don't know, I guess that allows you to put that as a, I don't know, a sorted array of numbers.
So
but I'm not sure how you get to E.
Okay. Yeah.
Oh, I see. Array then becomes in E your bit vector sorting of 32, and then this bit vector sorting. Okay, so I guess that's how you're translating the big V6 as J into the array stored at E.
Okay, you're sort of using the same the right thought process. But okay, according to your theory, this is some kind of a sorted array. But then the way to verify if your theory is right or not is like, the first number in this array is 49. How is 49 related to this big number here? And again, okay, the other clue here, Dave, is check out the actual for loop, right? So the way the for loop is using this number here, v6, right? Check it out. It's using it as a array, and then based on the offset. So, you know, at the first iteration of this for loop, I is equal to 0. So it's taking the very first byte of v6. And then at the next iteration, it's going to take I becomes 1. So once you add 1 to v6, it's going to take the next address, the next byte within v6. So that is how it's being used in the code. So what you have to figure out in terms of this translation, like you're saying, it's probably somehow related to this big number here, represented as an array. But how do you convert this this 49? What does this 49 represent in this number here?
So I don't know, is that the first value stored in the first address of the array?
First address of the array. Okay, so that's true. So you're right in terms it's the first byte in the array, but the other sort of important detail that you're missing is how will this V6 number right here, as a decimal, how will this be stored in memory?
Oh,
right there you go. Now things are clicking.
Okay, that's taking me back to data structures and algorithms.
Sure. It's this is a lot of. It took me a while too, Dave. It took me a while, but here I'm gonna walk through it. Right, let's just walk through it. But things are clicking, and now you're sort of thinking about, hey, wait a minute, what's the relationship, and how would you go about converting this number into an array? So what I did, oh geez, okay, let's leave that alone, and I will move here. So I'm going to use this website right here, Rapid Tables, and it's an online site that will give you conversion. So this is what I did, right? So this is the original decimal number for the V6. This is the decimal number, right? I put it in here, and then it gives me all these different representation, right? Hex representation and binary representation. So this decimal number right here, what it's going to look like within memory in binary is this. This is what these numbers will look like. So to get the very first number of this representation of integer, the first byte. So Dave, how many bits are in a byte?
8.
Thank you. Yeah. So 8. So that's what we do. We take the first 8 here. 1, 2, 3, 4, 2, 4. So this is 8, right? So we take 8. We jump into this other one, we put it into the binary, convert it, and then this first byte here converts to 49.
Well, okay.
Right? Let's just like follow the walkthrough, right? Let's just follow the walkthrough, and then let's see what happens in terms of so 49 was the value, right? We got the first, and then we put it here 49, and the first one is 49, right? Very first part of E is 49. And then next, this is super counterintuitive. This is why this is super challenging. It's totally counterintuitive, right? So now we get asked, what is in the second byte of the memory storage, right? So let's take, that's 4, 5, 6, 7, 8. So we take another 8, and then we go here again, put in the binary, boom, and then in decimal, this is 56. And then we go back here, the second value here is 56. So it seems very convoluted, and if I were to give you, if I didn't give you any more details, I just gave you, hey, this is a number, and then this is an array. Find the relationship. It's, for most people, I think that's almost impossible unless you give them the right context, right? But then if I told you, hey, Dave, this is a decimal representation. This number is in decimal representation, and this is an array that represents that. But this is the thing that is really confusing, is that this is also in decimal representation, but it's decimal representation for each of the byte. That's the part that's really confusing. The way this is usually done in most programming languages, this is represented as a hex value. That is usually how it's done. So this is how they usually do it, right? So once it's in a hex value, this is what happens instead. If it's in a hex value, then you would see it as this value right here. And then to get the first byte, you would just grab these two guys, and then you would put this in the array. And then for the second one, you would just grab these two guys and put this in the array. Because the binary and the hexadecimal, there's a direct relationship between them. For decimal, you have to convert it. You have to convert it to like, what's the base, what does it look like in memory, and then extract the bits of the memory. So that's why it's totally counterintuitive. But that's like the first very, very important step of being able to represent that within this data structure that Z3 expects, because this is how Z3 works. So again, that's one of the big challenges. And the next big challenges that we're going to have to deal with is, so if you remember, this is what I cut and paste, right, from my disassembler, my decompiler. This is what I cut and paste. And so all I have to do is I'm going to have to encode that within Z3 notation, right? So the first one is just a multiplication with 53. So this V6 value with that offset, which is going to be that J that you saw earlier, we're going to multiply it by 53. So that's all this is right here, right? We're going to multiply it by 53. The second one, we're doing a modulus 128, and then we are adding it. So that's all we're doing here, modulus 128, and then we're adding it with creds 2, which if you look earlier, this is what that's going to be represented as, this really weird global thing. And then finally, at the very last line here for D3, I'm first going to do this part right here, right? So what's happening here? First, it's going to be modulus, okay, 23. So this multiplying by 23, you see it here. You subtract 43. Let's see. Oh, okay. This is why I'm getting a little bit confused here. Oh. No. Okay, yeah, 48. Okay, so there's a 48 right here, and then we multiply by 23, and then we modulus 30, right? So all that's is most of it's there. So you can sort of see how the conversion process is not working, right? And then there's also this part right here where you're bringing it to the power of kk to the I, and that's where, let's see here, that is taking place right here. D to the %I, that's this k to the 2 right here. So basically, we have, see this comment code right here from the decompiler, I converted it to this kind of functionality. So I've encoded all of the equations now. So now I can solve it, right? So now I can run to solve it. So let me run Python that out. So now it's going to try to solve it. I encoded all the equations in the right format, and then it solves it, and then this is going to be the solution, right? So let me copy that. And okay, we go back to our rev here. And if we remember, let's just pull up that disassembly. And I think, this is almost done here. We go to this one. We go to this guy. Okay, right here. If we go back to him, the username is going to be Palash2, right? So we do Palash2. And just to show you, like, I don't have any funny business, right? You put in the wrong password, you get a login fail. So let's do it again, Palash2. And then I put in the code, and then you get the flag, right? So that was the right code. But to sort of really quickly summarize this, what did I do here, right? I went to the disassembly to sort of try to figure it out. I ran into this really complicated equation that was too tedious for me to solve manually. So then I used this very powerful Z3 library so I had to create my own Z3 script to encode the equation I was interested in, and then I had Z3 solve it for me. But check out, this is the thing that's sort of really interesting here. So, I got all of this from this walkthrough here, from this person, really good walkthrough, right? So he did his walkthrough, and from his script, this was a password he got, right? So let me try this password as well. So it's a different password. If you can sort of just eyeball it, right? It's a different password. So let's go here, run it, Palash2, and then we put in this is his password. It also works. So now the question should, like, a big red flag here is like, why can we have different passwords and it works? And so that's the question. And the answer to that is all that matters here. So it's not doing, so in this check for password function, it's not looking for an exact match. All it's doing is like, if this number in that memory location, after you do this equation, if that value, actually it's better if I look into IDA, if that value is equal to 0, after all the computation is equal to 0, that is going to be legitimate. So if so there's this problem with hashing insecurity where you have conflicting hashing, right? Where the same different inputs, if you get it to the same hash, then that's a hash conflict, even though the designer originally believed, oh, only this one input should give this one hash. But you have this problem of just different stuff because of the computation, giving you the same hash. That's called a hashing conflict. And use that. That's what you're seeing here as well. So this is basically doing some kind of pseudo hashing. And as long as v4 is equal to 0, it's going to accept it as a legitimate password. And then the very last thing I wanted to share about this write through is that when he ran his disassembler, so he ran the disassembler. This is the disassembly he got. And for the second function, the D function right here, he has this really funky, for his V3, he has this really fun, check it out, right? Shift 32, shift 25, shift 32, shift 25. That's what his disassembler has. If you look at my disassembler is modulus 128. This is the same binary, but so now what we're seeing here, we're seeing different versions of the decompiler giving you different results. Both are functionally the same. Both will get you the same results. But due to the logic of how it decompiles it, my decompiling was completely different from this person's decompiling. And if you go back to my original script here, right, I comment out his code. So this was his. This was his B here, right? His will work. And then this is my B, right? Totally different, but according to what it's doing, what the ultimate computation, you'll get the same value. And with that, I conclude my demo. Questions, comments?
Yeah. So I mean, obviously there's things there that sailed a little above my head a little bit. Oh,
yeah.
That's my dog. Just one.
Oh, yeah.
1 second, dog. But I was confused about 1 second.
No worries.
So, all right. Okay. He had a toy stuck between two boxes.
Oh, funny.
So when you were taking that long integer and you put it in to get like the binary and the hex.
Yes.
How did you know to start at the bottom? And maybe this is just me forgetting how arrays work.
That's a really important question. So the reason you start at the bottom is because this is Little Indian. This architecture is Little Indian. If this architecture was Big Indian, you would do the opposite. You would start at sort of the higher values or something like that, right? That's why.
Okay.
But
we just learned about this in school, so I should know this.
No. No, this is why we do these demos, right? And for me, this is what happened to me. For me, so this is a really good write-up. His solution is amazing, but he leaves a lot of the details out. He does not explain how he converted this number to this freaking bit array. So for me, I was like, what the, and usually the way they do this is they encode this in hex. That's why I want to tell you the way they actually do this, it's in hex, because once you do it in hex, then you can just take it and it's like, oh, I can see in the array it's 31 and then the array says 38. So all he's doing is he's putting these bottom ones first, and okay, that makes sense. But because Z3 is decimal, that's why you have this very funky conversion process. And I had it myself, like try to reverse engineer, how it worked. So that was my process for doing that. Okay,
so because it's little Indian, it's going to stick everything at the end.
Yes.
So the end is actually the beginning.
Exactly.
And I think the clue to that might have been you ran file on the binary.
Yes.
Did that show that to you in the beginning?
That's not really good question. So the way you would know is because on x86 architecture, including x64 Intel based architectures, those are Little Indian. That's how you would know based on what processor architecture you're using. And then other architecture, and also this is another important detail too, some network protocols, they have different Indian orders as well. And if you spend more time in GDB, this can get you really messed up as well. So let me go here to this assembly instructions right here. So in GDB, if you specify just like a say a byte, if you just specify a byte, it will probably give you if you specify a byte view in GDB, it will give you, say, just one. But then if you say, okay, I want the bytes for all of these hex, it will give you then 1, 31, 8. It will give you that way. But if you specify 32 bits, it will give you 3831 as the first one. So it will give you it this order, and but if you give it a byte order, it'll be 1, 3, 8, 3, because it's showing you a byte at a time. But if you specify 16, if you specify sorry, this was 16-bit. So, but if you specify 16-bit, it will give you it in this order instead. So, and sorry, this is a byte. So, you know, if you say a byte, it will give you 31. But then, so if you do byte by byte, it will give you 31 and 38. But if you say, okay, give me a word, right? Give me a word, which is 16-bit, then it will give you 38, 31. And again, you have to sort of know these kind of details to sort of understand the representation. Otherwise, the ordering of it will really mess you up. Okay. So that's what I got.
Wow, cool.
Yeah. Yeah, let me